Welcome back to our lecture series on the subject Material Science and Metallurgy. Until our previous lectures, we have discussed ferrous alloys. First, we have discussed about the steels, plain carbon steels, low, medium, and high carbon steels. Then we have discussed about the cast irons. In today's lecture, we talk about non-ferrous alloys. We start with copper-based alloys. Myself, Dr. Bhanu Prakash, Associate Professor in the Department of Mechanical Engineering at MLR Institute of Technology. So this is the overview of today's presentation. We discuss briefly about the copper material and its properties. Then we talk about the classification of the copper alloys, basically classification of copper-based alloys, in which we start with brass as the material. So further brass, depending on the composition, it is being classified. We will look at its classification. We talk about its microstructure, then properties, limitations, applications. Yeah. So finally, we will summarize and look at key takeaways. Copper, which is with the atomic number 29 and density is very low, 8.96 grams per centimeter cube, grams per cc, and which is having a melting temperature of 1085 degrees centigrade. So copper is known for its electrical and thermal conductivity. In most of our domestic applications, household applications, all the household wiring, electrical wiring is basically copper. We are using copper because of its excellent electrical conductivity nature. Then it is naturally corrosion resistant. We don't need to add any other alloying element. So it is naturally, by nature, it is corrosion free, corrosion resistant. It's having excellent corrosion resistance. And it is also antimicrobial properties. It offers antimicrobial properties. And so we use, traditionally we use copper utensils for our kitchen, right? So it offers certain health benefits as well. It kills the bacteria, that is what we are known for it. So these copper alloys are being classified into two categories. One is wrought alloys, and then we have this is basically copper based alloys, the classification of copper alloys. So alloying, why we do for alloying? So if you recall, so alloying is basically a combination of two or more materials combined to enhance the properties. That is our primary agenda. So properties such as strength, hardness, conductivity, and other properties. So we are trying to improve the properties. So copper based alloys. So we have two categories. First one is a wrought alloys. We have it, and then we have cast alloys. Wrought alloys are something which are deformable alloys, where you can see pure copper. This is a series with which it is called C10100 to C13000 is your series number. And then we have brasses. Brass is a combination of copper and zinc. And we have the bronze, copper and tin. So copper and tin. Then we have cupronickel, copper and nickel. So all these are wrought alloys which are deformable. Then we have cast alloys, in which you have yellow brass, and the series is C85200 to 85800 series, yellow brass. Then we have aluminum bronze, which is C95200 to 95800 series. These are the two primary cast alloys we have it. So we discuss mostly about wrought alloys here. We talk about the brass, we talk about the bronze, we talk about the cupronickel. So copper is a principal principal metal, which if it is alloyed with zinc, we get brass. If it is alloyed with tin, we get bronze. If it is alloyed with nickel, we get cupronickel. All are having principal metal is the copper. Copper is the fundamental metal or principal metal in these alloys. So pure copper, which is unalloyed, which is 99 percentage of purity, finds its applications in electrical wires, bus bars, and electrical wires and bus bars. This is a grade that we use it, C10100. Then C11000 we use it, which is relatively less, very small margin, but relatively less purity, which will be used in plumbing and roofing applications. These are both are pure copper. It is having its limitations. If you see the limitations of this, as we know, this is soft metal, copper, the pure copper, pure aluminum, and pure iron. All these are soft metals. We have to increase its strength. Iron is relatively stronger when compared to aluminum and copper. Copper is having its strength close to or in the range of 200 MPa, and it is poor machinability because of its when you try to machine it, it is gummy, so it will stick, it will not cut, but rather it is gummy, it will adhere to the cutting tool, so it is little challenging. It is having poor machinability. If you see the microstructure of the pure carbon, so sorry, pure copper, it is basically FCC structure, phase centered cubic structure, single phase FCC as a microstructure. So this is all about your pure copper. When we start with brass, brass as I mentioned, so copper is a primary element, primary metal into which it has been alloyed with the zinc. So zinc is the alloying element. So zinc, that will be ranging from almost 5% to 45% of the overall mixture. It is a zinc. So that much proportion we can add into the copper. It is soluble. Often modified with other alloying elements like lead. Then we have tin, aluminium, and nickel. So it has been often it is also been alloyed with other elements. So primary alloying element is the zinc. So it is not something new what has been come across. It has been used from BCE. So since 500 BCE, these brass material has been used, widely used. If you recall, Roman coins are manufactured out of brass, and early artillery equipment, that's also made out of brass. So some of the features, if you look at here, it will be offering golden appearance. It will be having golden appearance, and this golden appearance, this color will be varying with the percentage of zinc. As you vary the percentage of the zinc, the color will be varying here. And it offers excellent machinability. Unlike your pure copper, with the addition of zinc, its machinability is significantly improved. It is having excellent machinability, especially the leaded brasses with lead as the alloying element. Leaded brasses offers excellent machinability characteristics. So according to the percentage of the zinc, we classify the brasses into three categories. One is alpha brass, then we have alpha beta brass, then we have leaded brass. So in the alpha brasses, where the zinc percentage is less than or equal to 37 percentage, and alpha brasses are observed to be in FCC structure, alpha copper. So FCC structure, and which is basically cold worked. For example, you have the cartridge brass. So cartridge brass is which is grade with of grade C26000. So one of the examples for alpha brasses. Similarly, alpha beta brasses are having little higher zinc content, that is ranging from 37% to 48% of zinc, where you can see alpha and beta phases, both dual phases can be possible. So, are possible basically in this material. So, dual phases can be observed in the microstructure. and it is hot workable. So heat treatment has been possible. So what is example? Munj metal. Munj metal is a example for alpha beta process with a grade of C 28,000. We have leaded process where lead is being added in addition to the zinc. So how much percentage of lead? Lead is in the range of 1 to 3 percentage of lead is being added into the material. So which is example is free cutting brass. Free cutting brass with grade of C 36,000 is a classic example for leaded brass. If you see the composition again and the key property, so we have cartridge brasses, alpha brass, then we have the navel brass, then we have free cutting brasses, leaded brass basically, and we have the nickel brass as well. So here navel brass you can see the small amount of tin. So their grade numbers are been given here. So unique numbers, unique graded numbers are been given. So composition in the cartridge brass, which is example for the alpha brass, which is having less than 37 percentage of zinc. That is here you see 70-30 ratio in the cartridge brass, which are basically cold workable brasses. Naval brass is having alpha. It's a basically dual phase can be observed here. More than 37 percentage of zinc is present here, along with 1 percentage of tin also has been used here. So which is identical for sea water resistant. It is corrosion resistant, seawater, particularly seawater resistant, salty water resistant. And we have free cutting brasses, which is having zinc close to 35 percentage, and it is basically lead is being added here. So it is a leaded brass, free cutting leaded brass, 3% up to 3 percentage of lead can be added. So this will improve missionability to greater extent, missionability champion. And we have nickel with the addition of nickel. So together it is like 35 percentage together, zinc and nickel. So zinc is at 17 percentage and nickel is at 18 percentage. Together 35 percentage is the nickel brass, which is basically silver appearance. For nickel is bringing the silver appearance to the brasses. Otherwise it is golden appearance. So tin and aluminum additions enhances the corrosion resistance here. So tin and aluminum additions will enhance the corrosion resistance, whereas the lead improves the missionability but reduces the ductility. So lead is reducing the ductility, but it is improving the missionability here. So these are composition driven properties to the materials. So if you see the microstructure, so if we observe the microstructure of alpha brasses, we can see the alpha grains in the FCC structure, which is offering very high ductility, almost like 65% elongation is possible with this alpha brasses. And in the alpha beta brasses, we can see the soft alpha phase as well as the hard beta phases also can be observed. So dual phases can be observed in the microstructure, which is it's a trade-off between stronger but little less ductile because of the hard beta phases. They are stronger but little ductile. So still it is ductile but relatively less ductile as it is having alpha phase. Leaded brass, you can observe lead particles at the grain boundaries. In the grain boundary regions will be we can able to see the leaded particles in the microstructure. These acts like a chip breaker during the machining. So because of the presence of lead particles, so it's significantly improving the machinability characteristics of the copper alloys process. If you see the mechanical properties, so the underlying fact you can notice here, as the percentage of zinc is increasing, our strength is increasing, but the corrosion resistance is reducing. So this is having a de-zinkification risk, corrosion resistance. So as the percentage of zinc is increasing, strength is observed to be rising in the material, but its corrosion resistance is um, dramatically falling down. If it's the properties of alpha brass, dual brass, and leaded brass, so tensile strength is very high for alpha brasses, whereas and also the elongation is also very high, but hardness is relatively at a lower value, that is 100 HV. Okay, Vickers hardness basically. This is the Vickers hardness. Then we have alpha beta phase, that's the dual brasses, alpha beta brasses. We have tensile strength up to 400 is possible. Then we have elongation is 35% is possible, and it is offering good hardness, relatively among the best, we can say 150 Vickers hardness. So because it is that is coming from basically hard beta phase. You have hard beta phase, that's why it is shooting up your hardness value. And also, interestingly, your strength is also getting increased here. But it is, on the contrary, it is ductility or the elongation is getting down. So lead, it's bringing between the alpha and alpha beta brasses. So between you have your tensile strength, and elongation is also between, and hardness is also between. So lead you can put it between alpha and alpha beta brasses. If you see the corrosion resistance of brass, so de-zinkification, so selective zinc leaching in acidic or chloride environmental is possible. So if these brasses are brought into the acidic or chloride environment, so we can observe zinc leaching, so leading to the poor porous copper, so which will significantly affect its corrosion resistance of the material. What is the solution? So we have to use inhibited brasses, so where tin and arsenic has been added into this. Up to 1% of tin and along with arsenic can be used to prevent this zinc leaching problem. Then we have stress corrosion cracking, SCC. Stress corrosion cracking is another challenge. So ammonia or mercury exposure. So when these brasses exposes to ammonia or mercury exposure, so there will be cracking. You can observe it due to the stress corrosion cracking. It is called. So which because of which we have to avoid these brasses application in the chemical plants particularly. So if you see the advantages of brasses, so it is having superior machinability, especially with the leaded brasses, and it offers very good corrosion resistance. And this can be modified with the addition of tin and nickel. And it is aesthetically beautiful appeal. It will give you gold and silver finishes as possible. So silver finish that is coming from the nickel, and by default this is the golden appearance. These brasses. It has its limitations. Limitations, as we have discussed, like in the harsh environment, acidic or chloride environments, there is a chance that zinc leaching is possible. De-zinkification risks are there, and also lead toxicity is also present. So these restrictions for its applications in the electronics. This is having certain lead toxicity is also there. So it has its limitations in its applications. So applications, you we will be seeing in our day-to-day life so many applications of brasses. So it has its applications in the musical instruments, where we use the C2600 grade for manufacturing the trumpets and saxophones. Trumpets and saxophones are basically made out of brass. You have ammunition. We use the cartridge casings. Again, the same graded brass will be using it. Then for marine grade, you have C46400 for marine applications, and the propeller shafts and the bolts are being manufactured using these brasses. And plumbing applications, when in the case of walls and fittings, we often see the brass walls for tap and other applications. That is basically C36000 graded brass will be using it. And electrical applications, we have these connectors. Some of the brass connectors will be using it, and some of the terminals also being used with the brass terminals will be used. That is of C26,000, 23,000 graded brass will be using it. So brass doorknobs in hospitals kill the bacteria, which is basically antimicrobial. So we have the doorknobs that are used in hospitals. Basically, they are made out of the brass. So brass itself is having copper and brass is having its antimicrobial nature. So that eliminates that kills certain bacteria. So that's why we often observe hospitals using these doorknobs, brass doorknobs. If you see the manufacturing and processing, so first the casting, through the casting, sand casting has been employed for complex shapes such as walls have been manufactured. So hot working is another manufacturing process where alpha beta process are being manufactured through forging and extrusion process at higher temperature 600 to 800 degrees centigrade. Cold working where alpha brushes are being rolled or drawn into thin sheets or wires. Then we have machining also. Then leaded brushes are being employed in machining, which has been preferred for screw machining. So depending on the type of the material, we go with the different manufacturing or processing steps is being followed here. Some special brass alloys are also discussed there here, as we have seen the nickel silver combination, copper with the zinc and the nickel combination. So you have nickel silver. So 18% of nickel is been added here, so which is giving the silvery appearance for your jewelry. Then we have the aluminum brasses, again another classification, which is enhances the seawater resistance significantly, where 2% of aluminum has been added into the brasses. We have silicon brasses also for high strength and wear resistance applications. We have silicon brass of this grade, this particular grade. These are these are our special brass alloys, which is alloyed with nickel, aluminum, and silicon. So key takeaways. So the percentage of zinc defines properties for your material, where it stands out different phases in the material. So it can bring the alpha phases and it can bring the dual phases, alpha and beta phases also possible. So because of these alpha and alpha beta phases, its properties are different. When only alpha is present, so it is having relatively lower strength and higher ductility. But however, when the beta is coming in, so it's a hard material is coming in, so strength is significantly improving with good hardness. And but on the contrary, it is ductility has been relatively less. So it is a trade-off between the workability and the strength we have to make with the addition of zinc. Then leaded brasses are dominant in the machining of the zinc, so but it faces the environmental issues. Leaded brass. Then we have additions like tin and nickel additions, which combats the de-zinkification in the critical applications like in chemical and chloride applications, acidic environments. So this leaching problem, zinc leaching problem is there. So that can be eliminated by the addition of tin and nickel elements, which we have discussed. So brass is the alloy that rings like a bell, machines like butter, and resists the C. We have the C resistance is also there. C resistant grade brass is also there, and in our regular household applications, bells we use that is basically made out of the brass material, and in the machines, its machining characteristics. If you see, it's like a butter. It will very smoothly. It will have the machining characteristics. That's why the brass. It's an alloy that rings the bell, rings like a bell, and machines like butter and resist the seawater. These are some of the references that we have used. So here is your question for pondering. So why C36 and 36,000 grade is banned in drinking water systems in some countries? So C36,000 grade brass is leaded brass basically. So leaded brass is being banned to use in some of the drinking water systems in some countries, not all. What is the issue with it? So hint is also given. So the problem of lead leaching. So what is the problem with lead leaching? So you know the reason. So your response, I would like to see your responses in the chat. So with that, we will close for this brass discussion on the brass. And in our next lecture, we will see bronze. We will discuss on bronze. Thank you.